So we have the following problem. For positive integers n, Cn is determined by the rules C1 equals 1, C2n equals Cn, C2n plus 1 is negative 1 to the n, Cn, and we want to find the sum from 1 to 2013 of Cn, Cn plus 2. So you should not have any trouble figuring out what year this Putnam problem came from. Right? What year? For those of you who said 2012, you actually did get below the bar, needed to pass the class. So this is from 2013. So what's the first thing that should go through your mind when you see 2013?
Is it important?
Is it important? And if it's important, how is it important? So for something like this, the answer might depend on some properties of 2013. So we saw examples of this with the green chicken, with maybe dependent on what's the number congruent to modulo 3, what's the number congruent to modulo 4. Small things like that could matter. Or it could be maybe there's an explicit formula. If we're looking at the Fibonacci's, we have Benet's formula, and you give me any value of n, and I can find the formula for the nth Fibonacci coefficient. There's an exact answer. So the question is, how do we think the answer depends on 2013? What should step 1 be for this problem? Nope. Try small cases, right? And so one of the nice things about punching up answers is they actually do a table for small values. And so for those of you watching at home, you should have come to class, and then you would be able to see the answers. But here we see that when it's we're looking at the sum up to k, if k is equal to 1, 3, 5, 7, 9, 11, 13, 15, we keep getting negative 1 for the sum. What do you expect is true?
Why does it have a dash for 15 though?
Oh, they got lazy, right?
Yeah, right.
And so you can calculate what's going on for 15. But at this point, whoever was filling out the table, at this point they noticed the pattern. They may have noticed the pattern earlier and decided to just go a little bit deeper to be kind to the people that they're writing up the solutions for. But this is the advantage of doing small cases. It's amazing how many people don't try to do small cases and just start trying to attack the problem in full generality. So in terms of, we're now less than 24 hours from the start of the Putnam. In terms of what advice can I give that could actually make a difference, doing small cases by hand. That's one of the best things you can do, and try to sniff out a pattern. The more cases you do, the better chance you have of seeing the correct pattern. Over here, when we look at what's going on when k is even, so the even numbers, it's negative 1, negative 2, negative 1, 0, negative 2, I think, negative 2, 0. The pattern is flipping around a little bit more. And so it's a little bit harder to sniff out what's going on. Okay. Wait a minute, did I get something wrong?
It seems like even is going negative 2, negative 2, 0, negative 2.
Right. So let's look. Okay, so can you read me off the values for the evens? It goes negative. I just have a very bad angle. Okay, it goes 0, negative 2, okay. So maybe there's actually a very nice formula for the evens as well. How should we try to attack this now that we have a proposed formula? Induction. And so, in the interest of time, I'm not going to go through too much. I'll send you the link. It's not that bad. They look at the base case. And so, if k equals 1, it's not that hard to calculate. It's C1 times C3. And we know what those values are. And then for the inductive step, we assume we know the following. We now want to plug in going a little bit further in the sum. When we go further in the sum, the only thing that really changes is some of the very last terms. Right? Is we just get a little bit more at the end. And so how much more do we get? We get 2 more terms. And so we know the beginning stuff is negative 1, and now we get some expression for the end, and now it's playing games with the recurrence relation. And so at this point now, some algebra needs to be done to finish the analysis. And so I'm not going to go through the analysis here, but the idea was this was a really good example for induction. Why? Because when we go up to the next odd, we've only added 2 more terms. We have formulas for that, and if we just play with those terms long enough, we can maybe figure out what's going on. If you look at these formulas, there are certain numbers that are very easy to calculate. C of 2n is just C of n. So which numbers are all going to be the same? Not the evens. Powers of 2. Every time I multiply by 2, I don't change things. So all the powers of 2 are now together, and we know exactly what they are. Then we know immediately what happens for the ones right next to that. So one way to try to approach a problem like this sometimes is to say, well, can I maybe figure out what the formula is for C? If I can figure out the formula for C, then I can maybe evaluate the sum if the formula is somewhat tractable. And for some of the numbers, it's not so bad. It's also very easy in problems like this to get to the point where you are looking at more than you need. The problem is just asking you, what can you say about the sum up to 2013? It's not asking you to find a specific formula. That's one way to attack the problem, is to have a specific formula. But you may be doing more than is needed. So for problems like this, always think about the smallest provable unit. What's the least thing I need to get this problem to fall? And then think about, what do I have at my disposal that I can use to attack a problem like this? And one way might be, I actually can find a formula for the C, and maybe that formula is a tractable formula. If you can do that, by all means, approach the problem like this. We just need enough to understand a little bit of those extra terms at the end. But what I like about this solution is it is showing you how looking at a couple of cases has influenced the plane of attack. Okay, so I will, again, make this one available. I thought this was a really nice write-up. So, oops. What I would do now, let's see if I can, where is it? Nope. This is it here. Oh, here it is, okay. So here is, I think it's University of Iowa Mark Putnam contest. I've put a couple of copies over here for people to just grab. And I just thought we would just look at a couple of problems live as a class right now. So some of these are actual Putnam problems. Other these are extremely close to Putnam problems. So I'm an analyst. I know which ones I like. But I thought I would give you a chance to just put a few on the board and then just ask, is there anyone that people would like to discuss? What I like is now we don't know exactly which techniques we're supposed to use. That's how things are in the real world. I was going to say 1, but all right, we'll do 2. So evaluate the integral from 0 to infinity of the natural log of x over x squared plus 9 dx. Okay, any thoughts? Yes? One, I have a thought on how to approach, but 2, I'm not quite sure. So we want to evaluate this integral. We want to try to find good ways of attacking things. Now, one of the dangers is, is the integral well defined? So I saw one person shaking their head. Why is the integral well defined? It's on the exam, right? If this was not a well-defined integral, they would probably not give it to us on the exam. So the dangers are as x goes to infinity and as x goes to 0. Well, as x goes to infinity, log of x grows slower than any power of x. If you want, you can use L'Hopital's rule. And you'll see that as you go off to infinity, if you take the derivative of the top, you get 1 over x. You take the derivative of the bottom, you get 2x. You get 1 over 2x squared. That's going to go to 0. So this is decaying very rapidly as we go off to infinity. So it's going to be OK. What about as we go down towards 0? Is everything going to be well behaved? No. In fact, natural log of x goes to what? Sadly, it goes to minus infinity. Now, the denominator looks like 9 as x gets very close to 0. So near 0, this looks like we're integrating the natural log of x. So we could look at the integral from epsilon to 1, say natural log of x dx, and take the limit as epsilon goes to 0. There's a nice antiderivative for the natural log. It's x log x minus x. And then you evaluate this at epsilon and 1. When we put things at 1, there's no problem. The difficulty is when we have things at epsilon. The x over here is no problem. The difficulty is we have an epsilon natural log of epsilon piece. Well, fortunately, the log of epsilon is growing much, much slower than the epsilon is dying. So this product is going to go to 0. So the question is, what's the best way to see that this limit is fine? So we want to take the limit as epsilon goes to 0 of epsilon natural log of epsilon. I'd like to replace epsilon with something going to infinity and say that this is the same as the limit, say u goes to infinity, of epsilon is now 1 over u, and this is the log of 1 over u. What's the log of 1 over u? Minus log of u. So we get the limit as u goes to infinity of the natural log of u over u with a minus sign. And now this is something that I'm much more comfortable working with, because now I'm in the form of L'Hopital's rule. I have a ratio of two things going to infinity. With the epsilon log epsilon, can I use L'Hopital's rule directly here? No, I have a product of two things where one factor goes to 0, one factor goes to infinity. This is not in the form that you can use L'Hopital. So one of the biggest challenges frequently in stuff like this is to get things into the form where you can use what you know. And so it's all these different change of variables. So when we do a change of variable like this, we see that this is going to go to 0. So what does this mean that this is going to go to 0? This means the epsilon log epsilon piece goes to 0. This means the integral is well defined. This means this problem is well defined. You don't need to do this on an exam, but it's just good to know that it's well defined. All right, so now the question becomes, how would we handle something like this? Again, I have not looked at this problem. I'm looking at this for the first time with you. Partly it's because I was sick yesterday, partly because I think this is a good way to look at things. I have a guess as to what to try to do. I'm just curious if anybody has any other guesses. Let's consider simpler problems. What would be a simpler problem? Again, I have no idea if this will work, but what might be a simpler problem? I'm sorry? Yeah, if we drop the natural log of x, if we just integrated x squared plus 9, that's an arctangent. If we just had the ln, that's an x log x minus x. So one thing is to try to see, are there simpler functions that are related to this that we could understand? Well, if we're going to understand one of these simpler functions, then we are, in a little bit of trouble because we're putting in very large factors. So I have a product of things. When you see a product of functions, what rule do you think of? Integration by parts. And so I have to decide, what do I want to be u, what do I want to be dv? And it might be useful to make some changes, to add some factors. If I want to integrate natural log, what would I love to have if I was integrating natural log? I'm sorry? I'd love to have a 1 over x. If I'm integrating the x squared plus 9, what would I like to have there? I'm sorry? I mean, I can integrate 1 over x squared plus 9 directly. One thing I could try to do is I could write this as x over x squared plus 9 times the natural log of x 1 over x dx. If I do this, if I call this my dv, and if I call this my u, I'll then get like a log squared. I don't think this is going to work, but I'm just trying to show you ways you could try to attack a problem like this. If I tried to do that, I'd get a log squared. Over here, now I've got to do a du, I've got to do a quotient rule. I'm going to get a very high degree down there. So I don't think it's going to help us in this problem, but maybe we don't even need to do that. Maybe we should just do things directly. Yes?
And I was thinking if we're doing integration regards, we might want a solution with the u for ln of x, the du for 1 over x squared plus 9. So that the ln of x.
Right, and so that's actually just doing it directly and not trying to put in this extra factor. I think putting in this extra factor of x times 1 over x, I don't think it helps here. I was just trying to think of maybe nice ways to get some integrals. So for this problem, I don't think it works, but I think maybe we should just try integrating directly. So we want to integrate from 0 to infinity, natural log of x, 1 over x squared plus 9 dx. We could actually even replace the 9 with a 1 if we wanted to and figure out what the change would be. If we send x to 3x, then that would become a 3 here. We would have the ln of 3x. We would have like a minus a log 3. We could figure out what that is. We could replace the 9 with a 1 if we wanted to. So now when we have something like this, here's u, here's dv. So if we have u equals ln of x, and dv is 1 over x squared plus 9, then du would be 1 over x dx, and what would v be? It's going to be related to arctan, but we've got some issues because of the 9. So for problems like this, sometimes it's worthwhile to make changes of variables. And so we've got the integral from 0 to infinity of natural log of 3x times 1/3. Let's see, x squared plus 9 dx. So here, we'll do it like this. If we let x equal 3t, then this becomes the integral from 0 to infinity of the natural log of t plus the natural log of 3 over, now we'll get 9t squared plus 9, and dx becomes a 3 dt. So we can pull out a third, and we'll have the integral of the ln of t over t squared plus 1 dt. And then we'll have plus a natural log of 3 over 3, the integral from 0 to infinity of dt over 1 plus t squared. But we know how to evaluate this integral with arctangent. And so I think that this might be a really good trade to do and to replace the 9 with a 1. So this should be, I think, like pi over 4, something like that, or pi halves. So we'll have arctangent at infinity. So arctangent, so I think this is going to be pi over 4. So if we do that, it's sufficient to just understand what's going on with a 1. And now we get arctangent of x. So we would get the boundary term, so uv. Are we going to be able to deal with the boundary term? What do you think? So if we integrate by parts, we've got to deal with uv. So we've got natural log of x times arctangent of x. As x goes to 0, what does arctangent go to? The angle whose tangent it goes to 0, that boundary piece will be okay. But unfortunately now as x goes to infinity, we're going to have trouble. Right? We may be able to get around it by saying rather than going up to infinity, let's go up to a very large place. This main term is going to be getting really bad, but now we're going to have to integrate arctangent times 1 over x. I'm not really too comfortable about integrating arctangent times 1 over x. Okay, so I mean, it's not a bad thing to try integrating by parts for this, but it's not working out too nicely. Now we have natural log of x, x squared plus 1. But I like that we're integrating from 0 to infinity of x squared plus 1 and not x squared plus 9. Are there any symmetries we could possibly use? So sometimes it helps natural log of x over x squared plus 1 dx plus the integral from 1 to infinity of natural log of x over x squared plus 1 dx is to break up the integral. What's nice here is maybe we can get something if we switch x with 1 over x. And then get integration over the same region. So do we want to integrate from 0 to 1, or do we want to integrate from 1 to infinity? 0 to 1. All right, so if we want to do things from 0 to 1, we could let t equal 1 over x. Okay. And then over here, this second one becomes the integral. When x is 1, we have 1. When x goes to infinity, this goes to 0. The natural log of, so x then becomes 1 over t. So the natural log of x is negative natural log of t. X squared plus 1, well, x squared becomes 1 over t squared plus 1. Now what's dx going to be? Dx is going to be negative dt over t squared. Right? All right, well, now we have dt over t squared. Well, the negative and the negative reinforce. Oh, when we bring the t squared down in here, we get t squared plus 1 again. So it looks like it's going to equal exactly the same as this. Except what? It's negative. Right? Because we're integrating from 1 to 0. Here we integrate from 0 to 1. So when we put this all in, this is now the integral from 0 to 1 with a negative sign, natural log of t over t squared plus 1 dt. And over here we have the integral from 0 to 1 of natural log of x. Using the fact that it doesn't really matter if I call it x or if I call it t, it's the same thing, right? What should the answer be? 0. Now, of course, the answer is not actually going to be 0 because we actually have this little extra piece over here. So the fundamental problem that we should be looking at, I believe, has the answer 0. And the answer should be, I think, like natural log of 3 over 4 times pi fourths. So if we now integrate natural log of x divided by x squared plus 1, x goes from 0 to infinity. Hopefully this will come out as 0. Yes. Whew. Okay. All right, so there's the answer. All right, so what I hope is that this gives you some sense of how to approach a problem like this. This was not prepared. I did not make deliberate mistakes and misleadings. These were just the natural things that I thought to try. And to me, the first thing is there a nice integration by parts? I have a product of two things. Then is there a change of variables? The plus 9, why do I have the plus 9? I can get rid of the plus 9 and make things a plus 1 and make things a little bit cleaner. If we didn't do that, it might be worthwhile trying to do this argument where you now don't do it with a plus 9, removing the plus 9. You might then have to do a slightly different change. Rather than t equals 1 over x, maybe it's 3 over x or something like that. It's a nice exercise to try to make this work. But there's one thing I have going on in the back of my mind as I'm looking at this problem. What is the key thing I'm thinking about? And why am I willing to do this class without preparing? There's got to be a nice answer, right? This is a preparation. This is a Mark Putnam problem. There's got to be a nice answer. There's got to be a nice trick to do this. Is life like that?
No.
No, not even close. All right? Most problems you face in life do not have a nice answer or a nice trick to get to. But for all these problems, there's got to be a nice answer. Symmetry is a huge thing to look at. And so what people frequently do is they take a nice answer and they disguise it. They add lots of layers to it. You know, the Shrek model, okay? They add lots of different layers to try to disguise what's going on. And then they give you all the fluff around it. So really, fundamentally, we're integrating from 0 to 1 and then canceling it. If instead of infinity, if they put 2013 here, what do you think would happen? Wouldn't it be nice? We would not be able to do it. So whenever they give you a definite integral, frequently definite integrals have a lot nicer answers than indefinite integrals. That if you know the integrand, sure, you can handle it. But most of the time, you don't know the integrand. Okay? So there's a lot of good ideas here. A lot of it is when you have an integral, you know, my best advice I can give you is if you see an integral, try to look for a point of symmetry. And so here we're going from 0 to infinity. Well, going from 0 to 1 is kind of like going from 1 to infinity if I replace x with 1 over x. And the idea is, hopefully if I can do some kind of transfer like this, it's similar to like this bring it over method of integration where you get the same thing on both sides. You can then solve for it. What we were able to get here is very lucky. We got it with a negative sign. Okay. Any other questions or comments on this problem? Okay. As long as we did 2, I was going to say no because I started speaking just before you. As long as we did 2, I'm going to use professor's prerogative and choose number 1. Because I mean number 1 fits so beautifully after doing number 2. So we want to sum k goes from 1 to n of 1 over square root of k plus square root of k plus 1. What do you think is true about this problem? Has to have a nice solution. Now for this one, how could they have phrased it? Oh, they want us to evaluate f of 9999. And they're calling this f of n. Do you think there's anything special about f of 9999?
Yes. Yes. It's 1 less than a perfect square.
It is 1 less than a perfect square. And for a problem like this, squareness might actually matter. So the fact that it's 1 less than a perfect square could matter, because remember, the very last thing we have here is a k plus 1. So if you put in 1 less than a perfect square, the very last thing we evaluate at is going to be a perfect square. Any thoughts as to what we might do here? Yes?
Personally, I dislike square roots in the denominator. I would get rid of those.
Yes. And this is called rationalizing the denominator. So this is a technique that is, I think, frequently taught in high schools, yes? And people, for the most part, hate it. And it's not clear to high school students, why would you want to do this? The whole point of rationalizing denominators is to try to make things cleaner. And so here, this is the same as the sum, k goes from 1 to n, square root of k minus the square root of k plus 1. Now when I rationalize the denominators, I'm going to multiply by square root of k minus square root of k plus 1, square root of k minus square root of k plus 1. So we're using 1 equals square root of k minus square root of k plus 1 over square root of k minus square root of k plus 1. So we'll get square root of k is k, cross terms cancel, k plus 1 with a negative sign, so the denominator becomes a negative 1. All right, we can pull the negative 1 outside, and this becomes a sum, k goes from 1 to n, of the square root of k plus 1 minus the square root of k. It's a telescoping sum. Right? This is why I wanted to do 1. It follows really nicely from some things, and it's not that long to do this. So it's going to just be the square root of n plus 1, and what's the first term? square root of 1. So now do you see why they did not do evaluate f of 2013? Would it really have been that bad to give us f of 2013? No, in this one we can actually get a closed form expression. The idea that they gave us, though, 9999, is this a clue that somehow we're going to be getting a square root and nice? I think that is a little bit of a clue here. For this problem, I don't know if it's really needed, but it is a little bit of a clue. This gives you also a nice chance to remember we don't know how to do most sums. Most sums are really hard. The exceptions are that we know how to do the geometric series, arithmetic progressions, and I think telescoping sums might be the only other thing that we can do in closed form. I think that's basically our arsenal. While it's kind of sad that we can't do much, for the purposes of taking exams like this, it's actually good because you've got to somehow move it to one of these things. Right? They're asking you to evaluate this sum. They don't mean you to put into a calculator and calculate all those numbers and get the common denominator. There's got to be a nice answer for this. There's got to be a nice way of combining things. How do we know how to combine things? Geometric series, arithmetic progressions, and telescoping. So somehow we want to get a telescoping. The key insight is to know we want to get rid of the square roots in the denominator. And the reason is when things are in the numerator, you can split them up very nicely. 1 over a plus b is not 1 over a plus 1 over b. Okay. I have seen, I might have shown you, years ago, I was grading, and somebody divided by 2 and got a plus b equals c. Okay. You will see mistakes like this. This is one of the advantages of becoming a professor. You get to see really interesting mathematics.
If you do one of those like find x and then you circle x things, do you get points on the Putnam?
You might actually get a negative score for the first time ever. The Putnam committee.
I think I would be happier if being the first person to get a negative.
To be the first person to get a negative score in the Putnam. But so there's tendencies to do stuff like this. There's tendencies to try to manipulate exponents incorrectly. It's what do we know how to do? We know how to telescope. And so when you have a sum that you need to evaluate, try to figure out, can we telescope it somehow? Or can we come up with an explicit form for what's going on? Generating functions are great for stuff like this. All right, so there was a question to do number 5. Okay. So that continues the sum theme. Okay. All right, so number 5 is we have a sum and goes from 1 to infinity. Okay, this is a Putnam B3 though. Oy.
I got into closed form without the thingies. So it's more a question of how do you evaluate.
Okay. Okay, and here x is the closest integer to x. Okay. And so they say, for instance, the closest integer to pi is 3. Because pi is 3.14, it's very close to 3. The closest integer to e, which is 2.7, is 3 because e is closer to 3 than it is to 2. Yes?
Do they define closest for when it's not 0.5?
They don't. But the square root of n will never be 0.5. So if you had, good point, if you had the square root of n was equal to an integer plus 1/2, then if you square both sides, you would get n is integer squared plus 2 times integer times 1/2 plus 1/4. So the square root of n is never going to be halfway between. So they do not define it there. In real life, I think if it's 0.5, I think the rule is you round up. But doesn't matter too much. Okay, so over here, how do we handle this? All right, what was your attack?
I figured out like what the threshold was for when you go down, up versus down, and then
Okay.
like a double sum from k equals 1 to infinity, and then inside that it was like from n equals k squared minus k plus 1, k squared plus k.
Okay, so it's where does square root of n change? So n, and then like the closest integer to square root of n. So when n equals 1, the closest integer is 1. When n is 2, it's 1.4, so the closest integer is still 1. When n is 3, it's 2, because now this is about 1.7. And now clearly we can go all the way up to n equals 4, 2 squared, but then how far can we push it?
5.
So 6 is also 2. Okay, and then 7 becomes 3. Okay, so the question then is, how far can we push it? So if we look at n equals d squared, it's pretty clear what the square root of n is going to be and what the closest integer is. So we want to look at n minus a to n plus b, all closest to d. So is this how you're attacking it?
Yeah, for example.
Okay, so we want to basically see how far can we go down below d squared and still have the closest integer when we take the square root. So we want the square root of d squared minus a to be greater than or equal to d minus a half.
Yeah, I think they just said that you want like n minus, you want like, yeah, like root, if you're like trying to find like where n plus b is like the threshold, like root n plus b minus d to be less than d plus 1.
Okay, is that equivalent to this?
Yeah.
Because here's my number n, and I want to see how far down below d I can get so that this is still greater than or equal to 1/2. So if I then square things, I would get d squared minus a is greater than or equal to d squared, cross term is going to be minus d plus 1/4. So the d squareds cancel. We bring this over and we get d plus 1/4 is greater than or equal to a. So we can go all the way down to d. So is that what you ended up getting? Okay. So what we're trying to do is we're trying to figure out, let's get some information about how this function closest integer to the square root of n behaves. This goes back to how we started the class. Build a table, do some experiments, gather some data, get a sense of what's going on. What's nice is if these functions weren't here, if I just had the sum of 2 over 2 to the n, would that be any problem? No. Why would the sum of 2 over 2 to the n be no problem? I'm sorry? Be more specific. It's not just a converging series. It's a geometric series, right? This is one of our dream series, right? We know geometric, we know arithmetic progressions, we know telescoping. So the idea is if we're going to make any sense out of this, telescoping is going to be kind of hard with just plus signs everywhere. You really kind of need a negative sign for telescoping to work. So our only chance is that maybe there's a geometric series lurking in between. Or maybe a bunch of geometric series. All right, now we could go the other direction, and we want to go plus b. And now we want that to be less than or equal to d plus 1/2. And so we would now get, reversing the inequalities, and now we would get b is less than or equal to d plus 1/4. So I think we get, it goes from d squared minus d to d squared plus d. Yeah, because I was going to say we've got to be a little bit careful with. And then in terms of looking at something like this, we sometimes have to worry a little bit about going down from d plus 1 squared. And so we may be off a little bit slightly. So I will accept whatever you're saying right now rather than going through all the algebra. So the square root of n equals d implies what's the range for n? D squared minus d to d squared plus d. All right, that's the range. So now if you look at our sum, we now have the sum, n goes from 1 to infinity, of 2 square roots of n So here's the next question. Does it help us that we have this combination? Or do we want to break it up into two sums and evaluate the two sums? What are your thoughts? So do you think, so I don't know the answer. I'm just curious. What do people think? If it helps, I can give you an answer for both. Which answer do you want to hear first? I feel like the lawyer. What answer do you want, guys? Do you want an answer why it's better to have both of them together or to do it as two separate sums? I'm sorry? Together. Look, come on, guys. They gave it to you together. There must be a reason. They're doing this to be nice, and they're combining it. So if you look at them as a unified whole, it's going to be a lot easier. And it's very similar to all these other problems. They're trying to hide things. And if you resist the temptation to split it up and just look at it as a unified piece, it'll be much easier. Of course you should split it up. Are you crazy? They're trying to confuse you by putting them together. It's fun. We don't know how to do stuff like that. We know how to deal with the geometric series. They're giving you just two geometric series. Let's do it as two sums. Jesus. Okay? So I mean, again, you can make either argument work, and until you do the problem, it's not necessarily clear. The hope is that maybe somehow things become nice, but they're going to be strange powers of 2. This is going to be increasing. This is going to be decreasing. And I don't necessarily see a nice way of combining them. Maybe at the end of the day, there'll be some nice cancellation from combining them. I might try doing them individually. And so now, what we want to do is we want to sum over all d. And then there could be some issues when d equals 1, because when d equals 1, we can't, oh, well, actually, no, when d equals 1, we'll still be fine with this formula. So d goes from 1 to infinity. It could very well be, and that there's really no benefit of combining them. And now we'll have a sum. K goes from d squared minus d plus 1 to d squared plus d. Now the top becomes 2 to the d plus 2 to the negative d. That's the whole advantage of breaking it up like this. The bottom becomes 2 to the n. So it becomes 2 to the k, right? And so we have a finite geometric series. And we can evaluate the finite geometric series. And then the hope is that maybe somehow things are going to cancel out nicely. All right, so this becomes the sum. D goes from 1 to infinity. If we pull out the final bit at the end, we've got a 2 to the d plus 2 to the negative d over 2 to the d squared minus d plus 1. Then a sum, L goes from 0 to, it's either like 2d or 2d plus 1. Okay, so now when L equals 0, we start off at the very bottom, and we've got to go, if we go all the way up to 2d, I think 2d minus 1. Is this the sum you end up getting? I'm just pulling out the, I'm writing just k as d squared minus d plus 1 plus L, and L goes from 0 to whatever I need. So we now have this. We can evaluate this using the finite geometric series formula. And so when we do that, we get a sum d, the last manually turned of the semester. D goes from 1 to infinity, 2 to the d plus 2 to the negative d over 2 to the d squared minus d plus 1. And now we have the finite geometric series, so it becomes 1 minus 2 to the 2d minus 1 plus 1 over 1 minus 1/2. And so now we have a sum over d. All right. And so now the question becomes, is there some algebraic simplifications that come into play? We've got a 2 to the d squared. In terms of getting a closed form expression, that's going to be a little bit of a challenge. So, what is it? Anybody know the command in Mathematica for the closest integer? Good. Excellent. Round square root of x. So now let's sum of 2 to the f of n minus 2, oh sorry, plus 2 to the negative f of n, right? And then divide by 2 to the n. N goes from 0 to infinity, or 1 to infinity. So we'll see if Mathematica is able to, I'm curious to see in the last moment, can Mathematica get a nice form for something like this?
How would we do this by hand?
Well, now the question becomes, can we somehow get some nice cancellation coming through here when we look at it? The problem that scares me is having a 1 over 2 to the d squared.
It felt like a little cancellation, but it's still not big.
Yeah, and so, I mean, at this point, it's not a horrible formula. This is a very tractable formula in terms of it's going to cancel well. I mean, for me, I would almost use like Poisson summation or something like that.
What if we just handled the individual sums on D?
What do you mean by? So it's now 11:54. So anybody who needs to leave, by all means, feel free to leave without. But so for something like this, in terms of the final way of putting it. So,